Welcome back, my friends, to the show that never ends. We're so glad you could attend. Come inside, come inside. Welcome to the Storage Developer Virtual Conference. My name is Bill Gervasi. I'm the Principal Systems Architect for Nantero, and I'm going to be giving you an update on the JEDEC specification for DDR5 NVRAMs. Looking at the agenda, what I intend to cover today is we're going to look at the memory hierarchy and understand the baseline, agree on a baseline where we understand why we built the memory hierarchy the way we did. And then, in particular, what is it about non-volatility that is driving these system architectures? And how could we have changed the system architecture if we had more non-volatility? We're going to look at the NVRAM standard, which is coming, and understand how it affects the main memory. I'll give you a quick update on Nantero and our efforts to create the world's best non-volatile memory. I'm gonna then apply this to the system architectures and look at how the availability of these new memories can affect system architectures. And then I'm going to close with a call to action. You've seen this pyramid so many times, I'm sure you're probably tired of seeing it. The idea is that we have this game that we play that ranges from the registers inside the CPU, which are very small but very fast, out to much slower memories like hard drives, which hold much more capacity but have much longer latencies and are much slower. And the question is, why do we do this? Well, again, just establishing a baseline. I know you all understand this, but we do this because of the fear of power failure. And when that power fails, that we're going to lose the data that's in process. The entire industry is based on this fear factor. So we've made a lot of progress over the decades. We started out with tape backup. We take that data and we throw it off into a strip of Mylar with the magnets on it, and by gosh and by golly, we still have that data even if power fails. Then as hard drives came into the industry, we were able to move that data off of the tape drives into something a little bit more compact, a little faster. Then we got even smarter. As flash memory got affordable, we could start moving to solid state drives. And now we could have more solid state drives replacing or at least supplementing the rotating media of the hard drive. Over time, we got smarter about how to make these things more compact, remove some of the layers of latency, and get even faster with things like the NVMe memory modules. Some would argue that if you go and put a non-volatile memory in the DRAM channel, that you can also get another layer of non-volatility. Unfortunately, that still leaves a big chasm. And that chasm between the slow non-volatile memory on the DRAM channel and the CPU is the DRAM. And that is indeed the weakest link in the system. And so the problem being, of course, that the D in DRAM stands for dynamic. You lose power, that data is gone. So what are you going to do about that? Well, the way we deal with that at the system level is what we call checkpointing. So if you have a SDRAM system, which today, generally speaking, is going to be your DDR system, and then maybe you have just your NVMe or your SSD drives off over the PCIe. The checkpointing algorithm says you're going to be running along. Periodically, you have to save what's in process because you can't afford to lose that critical data. So when you've gotten that data stored off into the non-volatile media, if you fail, all you lose is what's in DRAM. You go back to your PCI-based drives, restore them back, and you can continue processing. So this brings us to what is NVRAM? Well, NVRAM is the first proposition to literally replace DRAM with a non-volatile alternative. And it sounds simple, and it is simple, but the ripple effect through the architecture is significant, and it's worth having this talk about. Let's look at that. What happens when we now go to an old paradigm of checkpointing But now we go to a non-volatile main memory architecture. This new paradigm literally means leave the data in place, that the checkpointing is no longer needed, because if power fails, you are guaranteed that that data will still be there when power is restored. And with data still in place, there's really no need for that checkpointing anymore. Now, let's temper that with a little bit of a reality check. Obviously, I'm not anticipating that all storage will go away. You're still going to have the need for SSDs and NVMEs for mass amounts of data to feed the much smaller DRAM or NVRAM memory core. However, there are a lot of applications where the data sets are not going to fit in memory, and there are system failures besides power fail that you do need to worry about. You do need to worry about system components failing periodically. So this is the reality that we want to exist in. Now, how do we address this? Well, first of all, is that data set not fitting in memory? That's application dependent. And especially if we can increase the amount of NVRAM that's in the DRAM channel, we can increase the number of databases and applications that will fit completely in main memory and reduce the need to page in and out of the storage media. Yes, there are system failures besides power fail. However, a component failure is way, way, way beyond power fail as a failure mechanism. So therefore, the regularity with which you need to do checkpoints can change dramatically. And finally, yes, storage is not going to go away, but what you use the storage for can change. If you eliminate checkpointing as a function of the storage and only worry about moving large data sets in and out, your performance characteristics can change pretty dramatically. And so, what I'm going to be proposing here is hardware changes to the system. And hardware changes are pretty darn cool, but I think we all know it's really software that moves the industry, not hardware. So let's talk about how this software is going to enable these new architectures. And you've probably seen this over the last few years. The introduction of things like NVDIMMs into the industry gave us that paradigm of non-volatile memory, albeit in a kind of clumsy way because it required things like supercapacitors and reduced amounts of memory and so forth. But at least the availability of that allowed system engineers to rethink what it was like if you had a non-volatile memory resource that was in the main memory channel. So DAX mode was invented. And what DAX mode did is it allowed you to move software away from the file system concept, away from mounting drives, and they're encouraging people to rewrite their applications to do file mounted drive, where it's file mapped memory. And so when you go to this model, it's just a small step to direct access mode. So once you've gotten memory mounted as a RAM drive, you can then easily make that step right over into directly addressing the variables in place in the new memory system. So this software migration began years ago, and it's a major enabler to understanding how NVRAM is going to dominate the memory channel. Now, like I said, drives are not going away, and drives have the same problem that main systems have: fear of power failure. And the way that SSDs deal with this today is with having massive arrays of capacitors built right into the drives. And those massive arrays of capacitors supply enough energy to keep the entire memory module active during power fail. So the model there is that you're running along and then power fails, your power regulator is going to kick in, getting that energy from the capacitors to keep the data alive while you move it from flash, from SDRAM over to the flash. And then sometime later, power comes back, Now, when power is restored, you can copy back from the SDRAM to the flash. Your drive is where it was when power failed, and now you can finally resume running. I've got to tell you, SSDs are absolutely going to love NVRAM. NVRAM allows the SSD to be completely rebuilt from scratch. You no longer need all those capacitors. You don't need the voltage regulator, because on power fail, the data can just be left in the NVRAM. So that also makes more room on the drive for flash. Customers don't pay you for those capacitors. Customers pay you to give them flash memory. So this allows you to put more flash on the SSD. And something that's a little bit more obscure is, how big is the cache for your SSD? Well, today, generally speaking, you have about a gigabyte of DRAM for every terabyte of flash. The size of the DRAM cache is literally a function of how many capacitors you can fit on the memory module, because that energy is needed to keep that system alive while you backed up a gigabyte of DRAM into the flash. When the data can just be left in the NVRAM, that equation goes away. So now if you look at your performance profile and you decide that 4 gigabytes of NVRAM for a terabyte of flash gives you a performance advantage, you can simply increase that cache size without fear, because you no longer have to worry about keeping energy to that module while it's operating. So now power can fail, power comes back, you just keep running as though nothing happened. Big change. So another reality check. In order to achieve the Holy Grail, to replace DRAM, the NVRAM must provide all of the capabilities of a DRAM. And that means it has to run at full speed. It cannot have a wear-out mechanism. It has to have at least the capacity of a DRAM, if not greater. And yet it still has to achieve the price of a DRAM. If you can hit those 4 bullets there, then NVRAM can become the ultimate memory in the industry. So I'm going to talk a little bit about NRAM, which is Nantero's version of NVRAM. It's trademarked, so we can't interchange the terms. But I'm also going to talk about some competitors. There is phase change memory, and there are new generations of that coming out. I've been reading about third generation 3D crosspoint coming. That'll have some additional characteristics. We also know that there are magnetic memories out there and some resistive memories. So because it enables the industry and encourages controller suppliers to support this industry and this shift to non-volatile main memory, this is why I began the specification of a DDR5 NVRAM. Okay, so what does that mean? When you put DDR5 and NVRAM together, what does that imply? What it implies is that you can start with the DDR5 SDRAM standard, which was just recently published. Now we're going to overlay that with an addendum. The DDR5 NVRAM specification is an addendum to the SDRAM specification that says the DDR5 NVRAM is just like a DDR5 SDRAM, and in addition to that, here are some other features that you can use. This makes it optional. This allows a DDR5 NVRAM to drop right into the DRAM channel as a plug-and-play replacement for DDR5 SDRAM. The controllers that exist today can talk to the new memory, and then over time, they can optionally add in the new features to take advantage of what NVRAM offers them. And what does that look like? So just on a high level, comparing what a DRAM and an NVRAM are like, the big ticket item is when you have a non-volatile core, you can get rid of refresh. And for those of you that have been working in this industry a long time and have been watching how refresh has begun to dominate the timing of our systems, and how we have to buffer data to compensate for the fact that the penalties of refresh have gone from 0.5% to 1% to 5%, up to 15% performance is now given up to just keeping the memory refreshed. So elimination of refresh is huge. And this is the first one that those memory controllers will definitely want to exploit. And it's as simple as turning off refresh. And they suddenly get that performance gain. Similarly, today, you go into self-refresh, you have to keep the power alive to the SDRAM. What the SDRAM does in self-refresh mode is that in the background, it has a little state machine that periodically goes through the memory and does read, modify, write cycles to the memory to boost the energy up in all those capacitors inside the DRAM. When you go to a non-volatile core, that requirement goes away completely. And so self-refresh can truly become a total power off state. Zero power self-refresh is a big win as well, especially in mobile applications. The NVRAM has to be timing compatible with DDR5 SDRAM. We are not looking to change the interface from the CPU to the memory. You simply can't do that and enter the market. So we have to face the reality that whatever we do with the DDR5 NVRAM must be compliant with the SDRAM timings. However, we are going to add some new features. And again, these are all going to be optional, but the data persistence starts to become very interesting. When you have a real-time task, or if you have a financial transaction task that's running on your processor, you want to make sure that the data is committed to the internal non-volatile array before you free that task off of the task list. Now we can add a definition for data persistence so that those tasks can be freed up by knowing exactly when that memory is permanently stored in the non-volatile array. Today, they have to do that via checkpointing. So your data commit cycles have to wait until data has been checkpointed from DRAM up to through the PCI to your NVMe or stored off in your Optane drive before the task is allowed to be freed. Now this can happen in nanoseconds instead of microseconds or milliseconds. Finally, we're not on the same treadmill that the DRAM is. The DRAM is apparently hitting a plateau in capacity, and the NVRAM technologies are just hitting their stride. So we anticipate that through the DDR5 generation, we're going to see the NVRAMs supply a lot more capacity per chip than the SDRAMs. So we have to think about that, compensate for that, but do it in a way that's compatible with the SDRAM. Also, it should be recognized that NRAM and phase change memory are not identical, nor is MRAM, nor is ReRAM. All of these memories have different characteristics, slightly different. There's a lot of overlap between them. They're all going to have non-destructive reads, non-destructive activations. They're all going to have this ability to hold the contents of memory. They're all going to have that ability to turn refresh off or at least slow it down. So what are the differences? Well, some of them are going to require a special command to do housekeeping. So for example, if they have a wear-out mechanism, they need to be able to have some kind of housekeeping to go off there and do repair, wear leveling, whatever it is they do in the background. Not all of the architectures leave the core intact. Some of them may have a destructive activation, in which case they will need to have things like a pre-charge to go back there and restore the array. Also, each of these architectures may have a different amount of buffering in order to hide some of these background operations. If there's a large cache or even big FIFOs in the device, you're going to need some kind of flush mechanism to determine when that data persistence has been achieved. And finally, there are going to be some differences in how we do the mapping of the DRAM protocol to NVRAM, so that could be reflected in things like the number of banks, the page sizes, and that sort of thing. The addressing is going to be slightly different between them. Here's an example. This is our architecture, the Nantero NRAM. We have what's called intrinsic persistence. What intrinsic persistence means is that anytime you do a write operation, from the time that the data crosses over the balls of the chip into the input FIFOs, a measured amount of time, which in this case is around 50 nanoseconds, you are guaranteed that that data reaches the non-volatile core and is permanent. Some other architectures, however, are going to be doing internal buffering. And that internal buffering is going to maybe collect up large numbers of write operations. And collectively then, what these architectures that have an extrinsic persistence will require a new command called the flush command. That flush command then gets issued periodically when the requesting task wants to know when it can get off of the task list. It issues that flush, validates that all the memory is consistent inside the non-volatile core, and then can be moved on. Some other applications are a lot more relaxed. They simply trust that the NVRAM is going to be able to eventually make the data persistent. And that can be done with battery backup, or just the fact that from when power fails, the energy on the bus is still valid long enough that maybe these chips can internally go through and do a flush. So in this particular case, these architectures will expect that the CPU will assert reset when it detects a power fail. And these devices, when they see reset, will start doing data collection internally, flush the results out to the non-volatile core, and be done by the time the power has gone away. Let's also look at the DDR5 SDRAM state diagram. Now, trust me, I'm not going to quiz you on this, but this is the state diagram as it comes out of the DDR5 datasheet. And you can see that there's a whole lot of stuff going on. But really, most of it you can ignore because most of it is just initialization and the tuning of the interface. So let's strip away all that stuff. Well, the SDRAM state diagram is still pretty complicated. You can see that you have this idle state, but off of the idle state, you go into a separate section of the state diagram once you activate. And so what is an activation? Remember, activation is when you take the contents of the core and bring them out to the sense amplifiers. And in the case of SDRAM, that's destructive because the core is made up of capacitors that discharge into the bit lines and come into the sense amplifiers. And then you can manipulate the sense amplifiers as your frontline cache, which is essentially your bank row buffer. But then you need to do a pre-charge, and when you pre-charge, it restores the contents back into the internal array. So that's why you have this fairly complex state diagram built up around the SDRAM. So let's now look at the equivalent state diagram for an NVRAM. And now this is an NVRAM that has a non-destructive activation. And let's do the same thing. Let's eliminate all the stuff that is just about initialization. All of a sudden becomes a very simple diagram. You come from the idle state. Now you can activate with a non-destructive activation, which brings the contents out to the sense amplifiers. However, the core is still there. The requirement for a pre-charge goes away. And from the idle state, you can do all the read and write operations that you need to do directly off of those sense amplifiers. And there's no need for a pre-charge to restore the contents back because the contents never went away. You could look at these two state diagrams and say, well, these aren't compatible. I thought you said NVRAM was going to be compatible with SDRAM. Well, literally, these are compatible. Any controller that supports the SDRAM state diagram can also support the NVRAM state diagram. You essentially no-op the pre-charges, you no-op the refresh commands, all of that stuff goes away, and you have a much more simplified diagram, which is close to a load store architecture. You still have row caches, but those row caches are simply to accelerate the access to the arrays. Now I mentioned that NVRAM is going to be exceeding the SDRAM capacity roadmaps. Now, the way that this manifests itself is the fact that the DDR5 SDRAM protocol has 33 bits. You do the 2 to the 33rd, and what you come up with is that the maximum supported density for a DDR5 SDRAM is 32 gigabits per die. Well, if NVRAM exceeds that, we're going to need to do something about that. But like I said, we're only going to do it in a compatible way. And the way we've done that compatibly with the existing SDRAM protocol is with an optional extension called row extension. Row extension means we're adding 12 more bits of addressing. So now the NVRAM standard can go all the way up to 128 terabits per die. So this will unleash vast amounts of additional capacity in your main memory channel. And again, thinking architecturally, for many applications, this is going to be a killer. Another change that's been made. If you look at the mode registers, now mode registers are those things that you use for setting up the device. So there are things like down in the bottom half of the mode registers for things, all your familiar terms, your CAS latency, your write recovery times, and so forth. Those are captured in the mode registers 0 to 127. However, there's also a new upper mode register set from 128 to 255 that holds new configuration parameters for things like training the interface for the very high speeds of DDR5. DFE, decision feedback equalization. This has been incorporated into each bit inside the DDR5 SDRAM. So DDR5 NVRAMs, to be SDRAM compatible, need to have the same set of mode registers, not only from 0 to 127 for CAS latency and so forth, but also the DFE settings. So 128 to 255 also need to be SDRAM compatible. What we've added to the architecture for both SDRAM and NVRAM is an upper page pointer. This upper page pointer allows us to have an upper page 0, which is the default, that is the SDRAM compatible upper register set. However, NVRAMs want to have an extended set of registers for things like the flush options. And the way we implement that is by setting a different value in the upper page register. Now we have the ability to expand up to essentially 255 new sets of extended mode registers. And again, forward looking and trying to make it easier in the future to tackle new architectures, to tackle expanding feature sets, and so forth. So Nantero is paying me to put all this together. So let's give Nantero their due, and let's look at what our implementation of NVRAM is looking like. Well, our implementation is called NRAM, like I said, and the way that Nantero NRAM works is it's an array of carbon nanotubes which switch freely. They're in a dielectric-free space, and what we're doing is using electrostatic forces to push carbon nanotubes one way or another. So it's like an electromechanical system that happens at the molecular level. Currently, we're showing this thing operating with a 5 nanosecond read or write time. It's totally balanced between reads and writes. And we've actually tested about 100 picoseconds in the labs as well. So currently looking at replacing DRAM, but yeah, we're looking at replacing SRAM eventually as well. The cool thing about the way that this mechanism works, because it uses the van der Waals barrier to determine what state it's in. When those carbon nanotubes switch upwards, they bond with the carbon nanotubes above them. And this results in a permanent change. And we're talking about thousands of years of data permanence here. So once that resistance changes, the carbon atoms essentially bond to each other and stay stuck in space, changing the resistance of the cell until the reverse energy disconnects them and pushes them back down. So we're seeing a nice consistent gap between the set and reset states, and very, very confident that this can be operating not only as a main memory, but you can see from those curves that multi-level cell has also been very successfully tested in our labs. So now you take that array and build it up into a cross point. So we internally create what's called a tile. And that tile has an X dimension, a Y dimension, and a Z dimension where we can stack carbon nanotubes vertically. So this is why we don't have the capacity limitations of a DRAM. Because we can go vertical, we anticipate being at potentially 16 times the capacity of a DRAM in the DDR5 generation. What we do is we take this tile and put the drivers and receivers underneath it. So we size everything based on the size of the transistors, but also on the flight times of the word lines and bit lines to match DDR5 timing. Then we just copy this tile. We proof out that tile and then copy it as many times as we need. For example, if our tile size is 64 kilobits and we want to make a 16 gigabit DRAM replacement, we just replicate that tile 256,000 times. Very simple process. Then we put whatever physical interface we want on it. That can be DDR4, DDR5, HBM, GDDR, LPDDR, whatever PHY you want to put in front of that to create the interface you want. And that's what's shown here in this DDR5 NVRAM reference design. You see all the stuff in blue is just your standard interface. Again, that can be DDR4, 5, and the rest. What we have here in an orangish or salmon color is the non-volatile core. So we swap out the capacitors of a DRAM core, we plug in the non-volatile carbon nanotube core, and now we have a non-volatile memory that to the outside world looks just like an SDRAM. Now I talk about our roadmap, and so here's what the roadmap is looking like. And I'm basing this on roughly a 60 square millimeter die size, which is your bulk commodity memory. We can build on a 28 nanometer process 8 or 16 gigabit parts just by determining how many layers of carbon nanotubes we put in. When we move to a 14 nanometer process, we're looking at 64 gigabits and 128 gigabits. Well, why is this transition significant? 16 gigabits is the maximum of DDR4 capacity today. 64 gigabit is actually kind of a step beyond where DDR5 tops out. And 128 gigabit is completely unsupportable in standard DDR5. So this is why it was necessary to introduce the row extension concept. When we move to 7 nanometers, we're looking at up to 512 gigabits per die. So that's where the 16 times the DRAM capacity comes from. Now, translating that to packages, DDR4 supports up to 8 die per stack. So you multiply these numbers and you can see we'll be able to package 16 gigabytes in each 11 by 11 millimeter package. When we move on to DDR5 allows 16 high die stacks. And now we're looking at 1 terabyte in each of those packages being placed onto a module. So this, again, starts to change how you think about system architecture when you can expand your capacity by a factor of 16, which just happens to align well with artificial intelligence demands, which are creeping into the cloud. Now, looking at what this looks like to the system, it's actually amazingly simple. You take a standard registered DIMM design, unplug the SDRAMs, plug in NRAMs, and now you have an RDIMM, which is non-volatile. You plug it into the channel, the system doesn't even need to know that it's not DRAM. So you can plug it into an unmodified system, run it as necessary, or optionally, you tune it for the features of the NVRAM. Now think about what I said about that capacity. When you go to 512 gigabit per die, now we're talking about a single memory socket being populated with 16 terabytes of DDR5 class storage that it holds its data for 12,000 years. Totally major change to systems architecture. And what are those things that you can take advantage of? Well, like I said, the big ticket item is elimination of refresh. Just getting rid of refresh is going to give you anywhere from 8 to 12 to 15% additional performance at the system level. But there are other things we're architecting into the NVRAM. Elimination of TPOP, the activations limits. Elimination of bank group restrictions, inner die delays. There's a whole bunch of stuff that you can do to tune the system to take advantage of the fact that you've gone from this refresh aware system to a simple load store architecture. I also want to talk something about the power profile. Now, I didn't want to violate anybody's copyrights, so I abstracted this from an actual vendor data sheet. This is what the vendor data sheet says about doing DIMM level DDR4 activations. You do an activate, you suddenly jump up to 2 watts per module. And then you do reads and writes, and the reads and writes are down at about a little under a watt, maybe 3/4 of a watt. And then you do another activation, so forth. So you're sitting there cruising at below 2 watts for the module operation. All of a sudden, your refresh timer kicks off, and you need to do a refresh. All of a sudden, now you have to compensate for a 7-watt spike in your system power. And this repeats. So the first 3 parts of this are going to repeat again and again and again. Finally, you might want to put your module into self-refresh. So what happens in self-refresh mode? Well, again, you have to keep the power on to the module, so there's going to always be some residual power. And then you're going to be getting hit periodically with 3-watt spikes every once in a while as the devices internally refresh. So what does this look like with NVRAM? Well, NVRAM simplifies this whole picture. First of all, you can see that you can get rid of the pre-charge operations. So you save that 1-watt burst every once in a while when you want to close a page. Also, you see that instead of stopping the system every 3.9 microseconds to do a refresh, you just keep running. You just keep doing reads and writes. And those are all much lower power than the refresh operation. Self-refresh doesn't exist. Now you can turn power off to the NVRAM and it holds its data forever. So that operation goes completely away. So this allows you to start thinking about redesigning your power delivery systems. When you no longer have to design everything around this 7-watt burst, which means that you have to stagger accesses between memory modules and all that other stuff, all that goes away. You're going to absolutely love designing power for NVRAM-based systems. So where are we going next? Well, obviously the DDR4, DDR5 roadmaps, the multi-hundreds of billions of dollars out there, but there are other markets as well. The mobile and automotive guys are desperate to get an LPDDR version of NVRAM going out there. They would love to have the 16 and 32-bit interfaces. They love the fact that there's 0 power standby, and then the temperature extremes, which I really didn't get into, but those are also important to the automotive guys. Artificial intelligence, machine learning, deep learning, all those architectures are primarily using a von Neumann style access to an HBM, high bandwidth memory. And those architectures tend to be very power hungry. They tend to run many, many watts, which is a problem if you have a temperature sensitive device. These are not temperature sensitive, so this will give a lot of benefits to the AI guys. Going into embedded applications, eFlash is already having scaling problems, so anticipate that NVRAM will be a natural replacement for eFlash in pretty much any kind of embedded application. So I can make a bold prediction that, assuming we're successful at deploying this, that NVRAM will emerge as the universal memory moving forward. And let's assume that that's the case. What is beyond NVRAM? Well, it turns out there's a lot of stuff happening in the industry to move towards fabric-based architectures. CXL is a great example of that. Now, that's not going to replace the parallel interface to DRAM or NVRAM, at least not initially, but it is enabling a second level of ways to access memory. which is out over a fabric. So now if I were to take those tiles that I showed you and strip away the DDR5 interface, what if I just gave you a media access layer that exposes the raw media? Maybe it does no error correction at all, because as we know, chip level error correction can hide system level failures. Maybe it does no sparing. Maybe you manage the sparing completely yourself. What if you're doing an AI engine that starts with 1,000-bit word, but then wants to boil it down to 1 bit of yes, that's a dog, or no, it's not a dog? The width of the interface is now under your control. You can do authentication, error correction, encryption, striping, and redundancy. All of those things can now be done in your management chip. And in particular, you can take that one step further and do processing in memory. Your AI engine could be inside your CXL controller. So let's think about total cost of ownership, because that's really where the rubber hits the road in making system level decisions. With an NRAM memory module, you've eliminated the data loss and power fail, and you've also increased your capacity. When you can put multiple terabytes on a memory module, you may, in applications that are capacity driven, you may be able to reduce the number of total systems you have. Completely eliminate this silliness of these complex battery backup mechanisms like the NVMs, and even things like the Optane drives. Those are redundant. They don't really store anything of use that is not already in an SSD or in the DRAM. They're just there to add some persistence and some bulk to the channel. And the mass storage that's needed for checkpoints, all that stuff can go away. And when that goes away, you can reduce your cooling requirements as well, because the whole system is generating a whole lot less heat now. So from a total cost of ownership standpoint, NVRAM is a home run. It's going to dramatically reduce the total cost of your system environment. So we can see that the introduction of persistent main memory can change everything about how you think about systems architecture and will enable whole new environments. Also, we see that people are already looking ahead to CXL, looking at integration right into AI chips. And so new models for data integrity are going to evolve based on the fact that you, for the first time, have a high performance, non-volatile memory that never wears out. And systems architectures are going to evolve. When this stuff starts shipping, you will start seeing major changes in how systems are designed. So I can hear my friend Nathan Brookwood saying, yeah, Bill, but when is this going to happen? Well, Nathan, let's answer it a different way. Since I can't talk about, I'm just an IP house. I can't predict when my customers are going to start shipping. I don't control their roadmaps. But let's put it this way. Let's assume that DRAM, that I'm right, and DRAM is topping out at 32 gigabit, maybe 60, some 64 gigabit, although the DDR5 protocol doesn't really favor that. And NVRAM has a roadmap to go to 16 times that memory capacity. What I'm going to do is turn the question around and say, what are you going to do if we're not successful? So I'm just going to say, I can't control my customers' roadmaps, but we all had better hope that they're successful at this because the industry desperately needs this technology. So let's close things up. The call to action is, this is still a development in process. Come to JEDEC, the Future Memory Task Group, JC42 Task Group number 5 or something like that. And come and join, get involved, help us drive the direction of this, help us deliver this to the market. Get your requirements known. When you start doing things like looking at the problem of chip level error correction, masking system level error issues, when you start looking at Rowhammer, come to us. Describe your problems, bring your data models so that we can all work together to fix the future and deliver something that will give you superior performance in the future. Quickly summarizing what we've talked about, we saw how the fear of data failure and the data loss is driving everything in the industry, but that non-volatility can take away that fear factor and change the way you think about systems. We see that NVRAM is intended to be a non-volatile DRAM replacement, which changes how you use that memory. And hopefully I've shown you that the Nantero NRAM is the best of the NVRAM architectures. We recognize that systems are evolving and we want to be the enablers for those changes. And finally, get involved. Work with us and get those changes to happen. And finally, what I'm going to do is take advantage of the fact that I have some of your time to introduce one last thing, and that is something called BRDG, Bridge to Connect. Bridge to Connect is a nonprofit organization that I'm involved with, and what we do is mentoring of university students involved in science, technology, engineering, and math. Twice a year, Bridge sponsors a technology event, and we bring students in, we bring in educators, we bring in local CEOs, and we'd like to invite you to attend as well. On October 20th, we have Michael Gearing from Raytheon, who is going to be talking on directions, applications, and the future of artificial intelligence. I'm sure you'll find his talk very useful. I think you'll find it's very interesting to get involved with BRDG, because let's face it, all of us are getting a little older, and it's time for us to pay it forward and make sure the next generation of students are going to be there to keep the momentum going. With that, I'd like to thank you for your time and wish you all well. I'll talk to you at the next conference. Goodbye.